In the 20th century, most vaccines took well over a decade to research, test, and produce. But the vaccines for COVID-19 cleared the threshold for emergency use in less than 11 months. The secret behind this speed is a medical technology that's been developing for decades, the mRNA vaccine. This new treatment uses our body's existing cellular machinery to trigger an immune response, protecting us from viruses without ever experiencing an infection. And in the future, this approach might be able to treat new diseases almost as quickly as they emerge. So how do these revolutionary vaccines work? The key ingredient is in the name. mRNA, or messenger ribonucleic acid, is a naturally occurring molecule that encodes the instructions for producing proteins. When our cells process mRNA, a part of the cell, called the ribosome, translates and follows these instructions to build the encoded protein. The mRNA in these vaccines works in exactly the same way, but scientists use the molecule to safely introduce our body to a virus. First, researchers encode trillions of mRNA molecules with the instructions for a specific viral protein. This part of the virus is harmless by itself, but helpful for training our body's immune response. Then, they inject those molecules into a nanoparticle, roughly 1,000 times smaller than the average cell. This nanoparticle is made of lipids, the same type of fatty material that forms the membrane around our cells. But these lipids have been specially engineered to protect the mRNA on its journey through the body and assist its entry into the cell. Lastly, the final ingredients are added, sugars and salt, to help keep the nanoparticles intact until they reach their destination. Before use, the vaccine is kept at a temperature of -20 to -80 degrees Celsius to ensure none of the components break down. Once injected, the nanoparticles disperse and encounter cells. The lipid coating on each nanoparticle fuses with the lipid membrane of a cell and releases the mRNA to do its work. At this point, we should note that while the vaccine is delivering viral genetic material into our cells, it's impossible for this material to alter our DNA. mRNA is a short-lived molecule that would need additional In the 20th century, most vaccines took well over a decade to research, test, and produce. But the vaccines for COVID-19 cleared the threshold for emergency use in less than 11 months. The secret behind this speed is a medical technology that's been developing for decades, the mRNA vaccine. This new treatment uses our body's existing cellular machinery to trigger an immune response, protecting us from viruses without ever experiencing an infection. And in the future, this approach might be able to treat new diseases almost as quickly as they emerge. So how do these revolutionary vaccines work? The key ingredient is in the name. mRNA, or messenger ribonucleic acid, is a naturally occurring molecule that encodes the instructions for producing proteins. When our cells process mRNA, a part of the cell, called the ribosome, translates and follows these instructions to build the encoded protein. The mRNA in these vaccines works in exactly the same way, but scientists use the molecule to safely introduce our body to a virus. First, researchers encode trillions of mRNA molecules with the instructions for a specific viral protein. This part of the virus is harmless by itself, but helpful for training our body's immune response. Then, they inject those molecules into a nanoparticle, roughly 1,000 times smaller than the average cell. This nanoparticle is made of lipids, the same type of fatty material that forms the membrane around our cells. But these lipids have been specially engineered to protect the mRNA on its journey through the body and assist its entry into the cell. Lastly, the final ingredients are added, sugars and salt, to help keep the nanoparticles intact until they reach their destination. Before use, the vaccine is kept at a temperature of -20 to -80 degrees Celsius to ensure none of the components break down. Once injected, the nanoparticles disperse and encounter cells. The lipid coating on each nanoparticle fuses with the lipid membrane of a cell and releases the mRNA to do its work. At this point, we should note that while the vaccine is delivering viral genetic material into our cells, it's impossible for this material to alter our DNA. mRNA is a short-lived molecule that would need additional enzymes and chemical signals to even access our DNA, let alone change it. And none of these DNA-altering components are present in mRNA vaccines. Once inside the cell, the ribosome translates the mRNA's instructions and begins assembling the viral protein. In COVID-19 vaccines, that protein is one of the spikes typically found on the virus's surface. Without the rest of the virus, this lone spike is not infectious, but it does trigger our immune response. Activating the immune system can be taxing on the body, resulting in brief fatigue, fever, and muscle soreness in some people. But this doesn't mean the recipient is sick. It means the vaccine is working. The body is producing antibodies to fight that viral protein that will then stick around to defend against future COVID-19 infections. And since this particular protein is likely to be found in most COVID variants, these antibodies should reduce the threat of catching new strains. This approach offers significant advantages over previous vaccines. Traditional vaccines contain weakened versions of live viruses or amputated sections of a virus, both of which require time-intensive research to prepare and unique chemical treatments to safely inject. But mRNA vaccines don't actually contain any viral particles, so they don't have to be built from scratch to safely adjust each virus. In fact, every mRNA vaccine could have roughly the same list of ingredients. Imagine a reliable, robustly tested vaccine that can treat any disease by swapping out a single component. To treat a new illness, researchers would identify the right viral protein, encode it into mRNA, and then swap that mRNA into the existing vaccine platform. This could make it possible to develop new vaccines in weeks, giving humanity a flexible new tool in the never-ending fight against disease.
The picnic near the lakeside in Chicago is the start of a lazy afternoon, early one October. We begin with a scene 1 meter wide, which we view from just 1 meter away. Now, every 10 seconds, we will look from 10 times farther away, and our field of view will be 10 times wider. This square is 10 meters wide, and in 10 seconds, the next square will be 10 times as wide. Our picture will center on the picnickers, even after they've been lost to sight. 100 meters wide. The distance a man can run in 10 seconds. Cars crowd the highway. Powerboats lie at their docks. The colorful bleachers are Soldiers Field. This square is 1 kilometer wide, 1,000 meters. The distance a racing car can travel in 10 seconds. We see the great city on the lake shore. 10 to the 4th meters, 10 kilometers. The distance a supersonic airplane can travel in 10 seconds. We see first the rounded end of Lake Michigan, then the whole Great Lake. 10 to the 5th meters. The distance an orbiting satellite covers in 10 seconds. Long parades of clouds, the day's weather in the Middle West. 10 to the 6th, a 1 with 6 zeros, 1 million meters. Soon the Earth will show as a solid sphere. We are able to see the whole Earth now, just over a minute along the journey. The Earth diminishes into the distance, but those background stars are so much farther away that they do not yet appear to move. A line extends at the true speed of light. In 1 second, it half crosses the tilted orbit of the moon. Now we mark a small part of the path in which the Earth moves about the sun. Now the orbital paths of the neighbor planets, Venus and Mars, then Mercury. Entering our field of view is the glowing center of our solar system, the sun, followed by the massive outer planets, swinging wide in their big orbits. That odd orbit belongs to Pluto. A fringe of a myriad comets too faint to see completes the solar system. Ten to the 14th. As the solar system shrinks to one bright point in the distance, our sun is plainly now only one among the stars. Looking back from here, we note 4 southern constellations, still much as they appear from the far side of the Earth. This squares 10 to the 16th meters, 1 light year, not yet out to the next star. Our last 10-second step took us 10 light years further. The next will be 100. Our perspective changes so much in each step now that even the background stars will appear to converge. At last, we pass the bright star Arcturus and some stars of the Dipper. Normal but quite unfamiliar stars and clouds of gas surround us as we traverse the Milky Way galaxy. Giant steps carry us into the outskirts of the galaxy. And as we pull away, we begin to see the great flat spiral facing us. The time and path we chose to leave Chicago has brought us out of the galaxy along a course nearly perpendicular to its disk. The 2 little satellite galaxies of our own are the clouds of Magellan. 10 to the 22nd power, 1 million light years. Groups of galaxies bring a new level of structure to the scene. Glowing points are no longer single stars, but whole galaxies of stars seen as one. We pass the big Virgo cluster of galaxies among many others, 100 million light years out. As we approach the limit of our vision, we pause to start back home. This lonely scene, the galaxies like dust, is what most of space looks like. This emptiness is normal. The richness of our own neighborhood is the exception. The trip back to the picnic on the lakefront will be a sped-up version, reducing the distance to the Earth's surface by 1 power of 10 every 2 seconds. In each 2 seconds, we will appear to cover 90% of the remaining distance back to Earth. Notice the alternation between great activity and relative inactivity, a rhythm that will continue all the way into our next goal, a proton in the nucleus of a carbon atom beneath the skin on the hand of the sleeping man at the picnic. Ten to the 9th meters, 10 to the 8th, 7, 6, 5, 4, 3, 2, 1. We are back at our starting point. We slow up at 1 meter, 10 to the 0 power. Now we reduce the distance to our final destination by 90% every 10 seconds, each step much smaller than the one before. At 10 to the minus 2, 1/100th of a meter, 1 centimeter, we approach the surface of the hand. In a few seconds, we'll be entering the skin, crossing layer after layer from the outermost dead cells into a tiny blood vessel within. Skin layers vanish in turn. An outer layer of cells, felty collagen. The capillary containing red blood cells and a roughly lymphocyte. We enter the white cell. Among its vital organelles, the porous wall of the cell nucleus appears. The nucleus within holds the heredity of the man in the coiled coils of DNA. As we close in, we come to the double helix itself, a molecule like a long twisted ladder whose rungs of paired bases spell out twice, in an alphabet of 4 letters, the words of the powerful genetic message. At the atomic scale, the interplay of form and motion becomes more visible. We focus on one commonplace group of 3 hydrogen atoms bonded by electrical forces to a carbon atom. 4 electrons make up the outer shell of the carbon itself. They appear in quantum motion as a swarm of shimmering points. At 10 to the minus 10 meters, 1 angstrom, we find ourselves right among those outer electrons. Now we come upon the 2 inner electrons held in a tighter swarm. As we draw toward the atom's attracting center, we enter upon a vast inner space. At last, the carbon nucleus. So massive and so small. This carbon nucleus is made up of 6 protons and 6 neutrons. We are in the domain of universal modules. There are protons and neutrons in every nucleus, electrons in every atom, atoms bonded into every molecule out to the farthest galaxy. As a single proton fills our scene, we reach the edge of present understanding. Are these some quarks in intense interaction? Our journey has taken us through 40 powers of 10. If now the field is 1 unit, then when we saw many clusters of galaxies together, it was 10 to the 40th, or 1 and 40 zeros.
We live in a 3-dimensional world where everything has length, width, and height. But what if our world were 2-dimensional? We would be squashed down to occupy a single plane of existence, geometrically speaking, of course. And what would that world look and feel like? This is the premise of Edwin Abbott's 1884 novella, Flatland. Flatland is a fun mathematical thought experiment that follows the trials and tribulations of a square exposed to the 3rd dimension. But what is a dimension anyway? For our purposes, a dimension is a direction, which we can picture as a line. For our direction to be a dimension, it has to be at right angles to all other dimensions. So a 1-dimensional space is just a line. A 2-dimensional space is defined by 2 perpendicular lines, which describe a flat plane, like a piece of paper. And a 3-dimensional space adds a 3rd perpendicular line, which gives us height and the world we're familiar with. So what about 4 dimensions, and 5, and 11? Where do we put these new perpendicular lines? This is where Flatland can help us. Let's look at our square protagonist's world. Flatland is populated by geometric shapes ranging from isosceles triangles to equilateral triangles to squares, pentagons, hexagons, all the way up to circles. These shapes are all scurrying around a flat world, living their flat lives. They have a single eye on the front of their faces, and let's see what the world looks like from their perspective. What they see is essentially 1 dimension, a line. But in Abbott's Flatland, closer objects are brighter, and that's how they see depth. So a triangle looks different from a square, looks different from a circle, and so on. Their brains cannot comprehend the 3rd dimension. In fact, they vehemently deny its existence because it's simply not part of their world or experience. But all they need, as it turns out, is a little boost. One day, a sphere shows up in Flatland to visit our square hero. Here's what it looks like when the sphere passes through Flatland from the square's perspective. And this blows his little square mind. Then, the sphere lifts the square into the 3rd dimension, the height direction where no Flatlander has gone before, and shows him his world. From up here, the square can see everything. The shapes of buildings, all the precious gems hidden in the earth, and even the insides of his friends, which is probably pretty awkward. Once the hapless square comes to terms with the 3rd dimension, he begs his host to help him visit the 4th and higher dimensions. But the sphere bristles at the mere suggestion of dimensions higher than 3 and exiles the square back to Flatland. Now, the sphere's indignation is understandable. The 4th dimension is very difficult to reconcile with our experience of the world. Short of being lifted into the 4th dimension by a visiting hypercube, we can't experience it. But we can get close. You'll recall that when the sphere first visited the 2nd dimension, he looked like a series of circles that started as a point when he touched Flatland, grew bigger until he was halfway through, and then shrank smaller again. We can think of this visit as a series of 2D cross-sections of a 3D object. Well, we can do the same thing in the 3rd dimension with a 4-dimensional object. Let's say that a hypersphere is the 4D equivalent of a 3D sphere. When the 4D object passes through the 3rd dimension, it'll look something like this. Let's look at one more way of representing a 4-dimensional object. Let's say we have a point, a 0-dimensional shape. Now we extend it out 1 inch, and we have a 1-dimensional line segment. Extend the whole line segment by 1 inch, and we get a 2D square. Take the whole square and extend it out 1 inch, and we get a 3D cube. You can see where we're going with this. Take the whole cube and extend it out 1 inch, this time perpendicular to all 3 existing directions, and we get a 4D hypercube, also called a tesseract. For all we know, there could be 4-dimensional life forms somewhere out there, occasionally poking their heads into our bustling 3D world and wondering what all the fuss is about. In fact, there could be whole other 4-dimensional worlds beyond our detection, hidden from us forever by the nature of our perception. Doesn't that blow your little spherical mind?